Good morning, sweet peas. So we are back for example 2 of exponential functions. We are currently working in our pink books. Look, I have mine on page 51. All right. So same example as a while ago, exponential functions, and it says 6.6 up at the top. This time we're on example 2 on waste. So if you will carefully look at the example on waste, and let's get right into it. Suppose the waste in tons generated by non-recycled paper and cardboard products over time is y equals 350 times 3 raised to the, look at there, 0.3 times x power. So once again, the exponent is the variable, it's the x. Our instructions say, sketch the exponential function on the coordinate grid below. How much waste did we start with? What's happening to the amount of waste over time? Now, just like on the first example, this is another exponential function. It tells us that, so we should not expect it to act like a line or a quadratic because it's not. It's going to act differently. And so we're going to figure out a pattern here by the next example about what all of these different values represent. But let's go to our Desmos and let's just put those values in. Y equals 350 times 3 raised to the 0.3 x power. So right over here, I'm going to say y equals 350 and then parentheses 3 raised. So remember, your exponent is your power key, which is shift 6, and that gives you your superscript. So it is 0.3 or 3/10 times x. And all of a sudden, there is my graph. So I'm going to scoot out, and I see, oh my goodness, what's happening here. All right. We need to fill in a table. So on our paper over here, we have values for 1, 2, 3, 4, and look at the y values. They're just growing just like leaps and bounds. And so we can see some interesting things are happening here. How much waste did we start with? And remember in example 1, we said at the beginning, that means time, which is x, is equal to 0. So let's just think about this. If x is 0, then 0 times 3/10 is 0. And then I have what? 3 raised to the 0 power. Well, anything raised to the 0 power is 1 because the 0 power represents division with exponents. Anything to the 0 power is 1 because, again, the 0 power represents one number divided by itself. And a number divided by itself is 1. So 1, and then 350 times 1, I think that's going to be 350. Let's go to the table and see. So what I can do, if you remember, is I can go up to, not add, I think it's right here. And what I can do is convert this to a table. And there it is, Shazam. All right, let's look. When x is 0, what's y? 350, just like we thought. And again, why? Because 0 times 3/10 is 0. So 3 raised to the 0 power is 1. And 350 times 1 is 350. Sure enough, when x is 0, y is 350. So how many were there at the beginning? 350. When x is 1, y is 486.6. So we'll probably round that. When x is 2, it's 676. So maybe we want to know what it is when x is 3. Looky there. See, we can type the numbers in, and the Desmos will generate the y values for us. 940. What about when x is 4? Look at there, 1308. So let's come over to our table and see if we have enough to fill in some of those values. And you know what? I think that we do. So let me see if I can scoot this over. All right. So what I'm going to do now is get my pen to working. And let's see if I can't get some better colors here. Because right now I'm in orange. So let's go to green. Green is nice. All right. So we're going to sketch this. And let's see. How much did we start with? Well, we already said that when x was 0, y is 350. And again, what does this stand for? Tons of paper. So how much waste did we start with? 350 tons of waste paper. That's an F. Sorry. There, that looks better. 0, 350. All right. So let's come over and pull off some more of these values. So I have 1 and approximately 487, and then 2 and 677, and then 3 and 940.7, so we'll say 941, and 4, and what does that say? 1308. 1308. And I need one more value, 5. And let's see if we can't figure out how that's growing. Okay, let's see if we can figure that out. So when x is 350, so when x is 0, y is 350. So a point right there. And then when x is 1, y is 487. And you're like, well, that's not on my graph. Well, you're right. So we're going to have to estimate 487 somewhere between 350 and 650 is going to be about right here. Okay. Then the next one is 2 and 677. So here's 2, here's 650. So 677 is just going to be about a hair up there. And then 3 and 941. All right. So that's 950. 941 is about right there. And then 4 and 1308. That's up here, about right there. And now I need a value for 5. And let's see. When x is 5, we're going to say 350 times 3 raised to that. I'm doing it on my calculator, so I don't have to toggle back and forth. 0.3 times 5. Oh man, 1819 actually is what that is. So when x is 5, 1819. So over here, x is 5. That is up here. All right. Do you see what's happening? At first, the y values are closer together, and then as x increases, the distance between each of the y values is increasing. So let's see. Does it look like, can you predict what's the next one going to do? Is it going to flatten out? Is it going to come upside down like it does with the quadratic? It's not going to go straight. What's it going to do? All right. It's going to do that. It's going to grow bigger and bigger and faster and faster. Yeah. So what's happening to the amount of waste over the time? Well, it's increasing, yes, but it's not increasing at the same amount each time. How could we find out what it's changing by? Well, before we could see easily on example 1 up here that we did the biology example that it was doubling. But this one, it's a little harder to tell because from 350 to 487, from 487 to 677 to 941, it's a little harder to see. Well, it's not doubling, and I'm looking up here at these numbers. Well, it's not tripling. Obviously, this 0.3 is going to have some kind of effect on it. So here's how we can find out what's happening. It's a constant ratio is how it's growing. So what do I multiply 350 by to get 47? What do I multiply 47 by to get 677? So we're going to take the second one, 487, divided by the first, 350. And let's see what we get. So 487 divided by 350, and I get 1.39. All right. So 1.39. All right, so now let's see. Is that work to get from the second one to the third one? All right, let's find out. 677 divided by 487 equals 677 divided by 487. Guess what? 1.39. And I'll just tell you for the sake of time that if you went in and tested each one of these, it would be approximately 1.39. We have to round it because the further decimals down that are rounded are slightly different, but it's approximately 1.39 each time. So it's increasing by a constant rate. I'm multiplying by the same thing each time. And again, in example 1, we were multiplying by 2. In this one, we're multiplying by 1.39. And how did we find that out? We took the second number divided by the first and got the ratio. And we checked it again. And how did we find out for this one? We took the third number and divided it by the second. Third number divided by the second. We could do 941 divided by 677 or 1308 divided by 941. Each time it's increasing, multiplying the past number by 1.39. And that's why it's not growing linearly. It's not growing in a quadratic curve, but each time it's increasing at an increasing rate of 1.39. So that's example 2.